Hello everyone, I am Ömer Faruk Tuna from Işık University Istanbul, Turkey. Today I will be presenting our latest paper titled Unreasonable Effectiveness of Lost Hidden Layer Activations for Adversarial Robustness. This is a joint work with Ferhat Özgür Çatak from University of Stavanger and my PhD advisor Taner Eskil from Işık University, Turkey. Before moving forward, I would like to mention about the two important papers which really inspired us. Within our study, we had a chance to improve the solutions offered by the first paper and find a simple yet effective solution to the paradox which has been raised by the second paper. The existence of adversarial examples is a phenomenon first observed by Sergey in 2013. After one adds a small perturbation on a correctly classified image like this dog, a state-of-the-art neural network would misclassify the perturbed image as a sports car. The perturbation applied to the image is often visually imperceptible to the human eye. There are many motivations why this phenomenon attracts so much attention. For example, image classification has been applied to autonomous vehicles. Suppose a model is trying to identify a stop sign. Then the car will stop after it sees such a sign. However, with a little perturbation which cannot be identified by human regulators, the model misclassifies it as a sign for speed limit. Then a tragedy might happen. Therefore, we should pay highest attention for securing the AI models against such kind of threats. We now introduce various types of adversarial attacks. First, it can be grouped by the attack objective. In the untargeted attack scenario, the attacker perturbs the input image, causing the model to predict a class other than the actual class. In the targeted scenario, the attacker perturbs the input image so that a particular target class is predicted by the model. Researchers commonly use three types of metrics: L2, L-infinity, and L0. L2 distance is the standard Euclidean distance. L-infinity distance is the maximum change to any of the pixels. And L0 distance is the number of distinct pixels. The last criteria for grouping the adversarial attacks is the threat model. White box adversarial attacks assumes access of an attacker to the model details like architecture and weights. Under this threat model, researchers have mostly proposed gradient-based approaches to generate adversarial examples. And there is also the black box threat model, where the attacker does not have access to the model details, and in this threat model, the attacker can only access the output scores or decisions. Within this study, we will be focusing on white box setting and aiming to find a defense solution to both gradient-based targeted and untargeted attacks. Here is a table of existing algorithms for adversarial attacks in white box setting. As you can see, various attacks exist for the two types of objectives and three types of distance metrics. All the attack methods except the Deepfool attack are gradient-based and exploit the gradient of the model to craft adversarial examples. Whereas the Deepfool attack is formulated on the idea that neural network models act like a linear classifier with classes separated by a hyperplane. Now we will briefly talk about adversarial defense methods and start with adversarial training. It is an intuitive defense method in which the model's robustness is increased by training it with adversarial samples. This strategy can be described as a mini-max game as formulated here. The inner objective is maximized by using the most powerful attack possible, which is mostly approximated by various adversarial attack types. In order to reduce the loss resulting from the inner maximization step, the outside minimization objective is used to train the model. Although adversarial training is accepted to be one of the most powerful defenses against adversarial attacks, adversarial trained models are still vulnerable to attacks like Carlini and Wagner attack. Here comes the defensive distillation technique. Although the idea of knowledge distillation was previously introduced by Hinton et al. To compress a large model into a smaller one, the utilization of this technique for adversarial defense purposes was first suggested by Papernote et al. The algorithm starts with training a teacher model on training data by employing a high temperature value T in the softmax function. Then, using the previously trained teacher model, each of the samples in the training data is labeled with soft labels calculated with temperature T in prediction time. The distilled model is then trained with the soft labels acquired from the teacher model and again with a high temperature T value in the softmax. When the training of the student model is over, we use temperature value as 1 during prediction time. The important thing about this technique is that defensive distillation forces the model to make a high confidence predictions. Although defensive distillation seems to work on standard gradient-based white-box attacks like FGSM, BIM, etc., it was shown that more effective attacks like Carlini and Wagner can break this technique. And later it was shown that even simpler attacks like targeted GSM attack could defeat the defensive distillation strategy. But unfortunately, the authors did not provide a mathematical proof. And it took for a while for the research community to understand mathematically why this method works for some type of attack algorithms and does not work for others. Then the mystery is solved. The actual reason of success for this kind of attacks against defensively distilled model is shown to lie in the targeted nature of these attacks. Katzer et al. Provided a mathematical proof that defensive distillation can only work for untargeted attacks and defensively distilled models will always be vulnerable to targeted gradient-based attacks. Within the next slides, we will try to understand the real reason for this and try to come up with a solution. To understand the reason why defensive distillation does not work for targeted attack case, it might be good to revisit the architecture of a standard DNN-based classifier. In the standard DNN-based classifiers, the convention is to omit the activation function in the output layer and directly apply the softmax function on the logits to get the probability scores for each class. One last thing to cover before we continue is the notation we use within our paper. Capital D denotes our dataset. K denotes the number of output classes. Xi and Yi are the ith input and output respectively. OK is the one-hot encoded vector with only kth index being 1 and 0 for the other indices. And lastly, pk represents the probability output score of any output class with index k. Gradient-based adversarial attacks try to exploit the gradient of the loss function j with respect to the input sample x. And what the attacker is trying to do is to use dj dx to maximize j. We know from chain rule that dj dx is equal to dj dz times dz dx. Therefore, for any target class k, the gradient of the model loss function with respect to the input image is directly proportional to dj dzk. And we can calculate the derivative of the loss with respect to the kth logit using below equation. And this equation is actually the difference between the final probability score and the label value of the associated class. Formal derivation of this equation is available in the extended version of our paper in archive. You can visit Appendix B for the gradient derivation of the cross-entropy loss coupled with the softmax activation function. Now it's time to revisit the problem with defensive distillation technique. For untargeted attack case, the model makes high confidence predictions in favor of the predicted class, therefore p-true approaches 1. And since the label for the true class is 1, dj dz and therefore dj/dx approaches to 0. And this is why the technique works for untargeted attack case, because the attacker cannot exploit the gradient to craft adversarial samples. But for the targeted case, again, we have to make dj/dz to become 0 for target class. And the way to achieve this for standard DNN-based classifiers is to make target probability p-target to be very close to 1, to make the previous equation equal to 0, and which obviously contradicts with the learning tasks. Therefore, there actually exists a dilemma between masking the gradient of the model for targeted attack case and achieving the task of learning for the model at our hand. To overcome the previous problem, we propose to use either of the two commonly known nonlinear activation functions, sigmoid or tanh, on the logits of the model as shown here. The important thing here is to apply high temperature value to these activation functions during learning process and use the model by ignoring the temperature value at prediction time, just like the defensive distillation technique. Now I would like to share the reason why we choose and use these activation functions at the output layer of our proposed architecture. The first reason is that derivative of these activation functions can be simply expressed in terms of themselves. And the second reason is that derivative of these activation functions approaches to 0 when the output of the activation functions approaches to their maximum and minimum values. After our proposed modification, the output of the last layer will be z hat, where z hat equals tanh z, or z hat will be sigmoid z, depending on the chosen activation function. Based on this modified architecture, derivative of the model's loss with respect to input image under gradient-based attack against any class K can be formulated as shown here. When we check the gradient calculations on our proposed architecture, in case of sigmoid function, the previous equation can be formulated as shown here. And in case of tanh function, the previous equation can be reformulated as here. And please note that our method forces z hat k to be 0 or 1 if we use sigmoid activation, and 1 or -1 if we use tanh function. Because during the training of the DNN, we force z hat k to be at its maximum possible value for the true class in order to maximize the final softmax prediction score. And similarly, we force z hat k to be at its minimum value for the other classes. So if you replace z hat with 0 or 1 in this equation, the derivative will be 0. And if you replace z hat with 1 or -1, again you will see that the derivative will be again 0. Therefore, using our proposed method, we can always make dj/dx approach to 0. This way, we can successfully zero out the gradients of the model for gradient-based targeted and untargeted attack threats. After providing a mathematical proof about why our proposed architecture will work for standard gradient-based white box attacks, we would like to give you a visual explanation as well. For this, we made a simple experiment and drew the loss surfaces of various models using two directions. One for the direction of the model's loss gradient and one for the same random direction. We know that a normally trained model is vulnerable to gradient-based white box targeted and untargeted attack threats. And the main reason for this vulnerability lies in the ability of the attacker to successfully exploit the loss function of the model as shown in the upper diagram. Again, we know that defensive distillation can only prevent untargeted attacks and will be vulnerable to targeted attacks. As you can see in the middle part of the picture, the loss surface is not flat for targeted scenario. And for our proposed architecture, the loss surfaces are flat for both of these scenarios. And this way, the attacker cannot exploit the gradients of the model to generate adversarial samples. Now you see the final probability scores of various models. We already know that the prediction scores of a normal model will be between 0 and 1. And we also know that defensive distillation forces the model to make high confidence predictions, and this is why the prediction scores will be very close to 1. However, for our models, if we use sigmoid function in the last layer, maximum prediction score will be 0.232 and the minimum prediction scores will be 0.085. And if we use tanh function in the last layer, maximum prediction score will be 0.45 and the minimum prediction score will be 0.061. Now we share the experimental results of our study about the success rate of attacks against various models. When we check the results, we observe that normally trained models are vulnerable to both targeted and untargeted attack types, whereas defensively distanced models are vulnerable to only targeted attack types. And our proposed models, which we call squeezed models, provides a very high degree of robustness to both targeted and untargeted attacks. This success results from the effectiveness of our models in zeroing out the gradients in both scenarios. One other thing worth mentioning about the results of our experiments is that in addition to gradient-based attacks, our proposed models exhibit excellent performance against Deepfool attack as well. Generally, the reason behind the success of Deepfool attack against standard DNN classifiers is the linear nature of these models as argued by Goodfellow et al. However, since we introduce additional non-linearity to the standard DNN classifiers at the output layer, the Deepfool attack algorithm fails to succeed in crafting adversarial samples compared to normally or defensively distilled models. And this is the results on CIFAR-10 datasets. We again see a very high degree of decrease in the success rates of these white box attack algorithms, which once again shows the effectiveness of our proposed solution. To summarize, the main contributions of this work are: we propose an effective modification to standard DNN-based classifiers, which enables natural robustness to gradient-based white box targeted and untargeted attacks. And we show that our simple yet effective method can block the gradient-based targeted attacks without impairing the ability of the model to learn. Finally, we experimentally showed that adding non-linearity to the last hidden layer provides robustness to some other types of attacks like Deepfool.